Okay, thank you very much. It's really quite a pleasure to be here. Thank you for inviting me. Nothing really beats coming to Minneapolis in January, especially when it snows every day that you're here. Actually, it's not much better in Boston, so there's really nothing to complain about. I'll just make a quick follow-up before I start my talk to something Mark said, as I mentioned to him when we were chatting before. This complicated title is actually a kind of a remnant of the days where I had to dress up the titles of my papers to make them look like they're very complicated and had nothing to do with sports typically, because back in the 90s, universities typically didn't really value contributions to sports and statistics. These days, you could be a little bit more upfront about it and not disguise it quite so much. Anyway, what I want to talk to you about today, and I want to warn you in advance, this is actually a technical talk, so please bear with me. I'll try to do my best to explain as many of the statistical concepts as we go along, but if you're getting confused, please stop me. This was work that was contracted by the US Olympic Committee. They were interested in being able to set up rating systems to monitor their athletes, US athletes, as well as international athletes, for the purpose of trying to estimate how strong competitors were so that they could decide on off-cycle competitions, not on the Olympic competitions, when to actually send their athletes to international events. So, for example, that they wouldn't get blown away by sending to one event versus another event. So if they had the choice between sending their athletes to certain events, they would prefer to send them where the athletes would do well. So that was part of the work that involved what I'm going to describe to you today. I ended up doing the work with my student, John Hennessy, who had ended up with the Houston Rockets and is now starting at Google. So by means of introduction, there are lots of competitions in which the outcome of the competition is a rank ordering from multiple players involved in the competition. So in games or races such as human races, car races, horse races, or games like poker, gymnastics, diving, and golf, typically what you end up having as a result of the competition is a rank ordering. So this is different from, say, head-to-head games where you only have two competitors involved in a game and you're just seeing which one is better. So now we're looking at these multi-competitor games where the outcome is a rank ordering. Of course, this applies to other settings as well, where you have non-sports settings where, like, say, beauty pageants, you have eliminating individual beauty pageants one at a time, grants, scholarships, and so forth, all involve rank orderings as outcomes. And that's what I'll be focusing on. So I want to be able to recognize in these situations where you have rank orderings that the competitor abilities might have strengths that are changing over time. So they're not constant over time. I want to be able to account for their abilities changing. It's actually somewhat surprising that there's actually a fairly limited amount of work in this area on time-changing abilities in the context of rank-ordered game outcomes. There's plenty in head-to-head. I've done a fair bit of work in that area, and I then just started getting into the rank ordering space. So what I'm presenting to you today is kind of the beginnings of some of the work in this area. So just an outline of this talk. I'm going to be giving the motivating example is from one of the US Olympic Committee's interests, which was to analyze downhill skiing, alpine downhill skiing for, they have women's and men's compete separately, and I'll be focusing on the women's competitions. I'll be describing the statistical model for analyzing these data. I'll be describing a Bayesian statistical model for how to actually estimate the unknowns in this statistical model. And then the material up to that point is actually not particularly novel. The part that is novel in what I'm going to be describing to you is this bullet item right here, which is performing an approximate way of what is considered to be sort of the classic approach of estimating the statistical model parameters using an approximating algorithm. And so this is going to result in a rating system for multi-competitor sports, which I'll describe the main components for you. I'll be describing a little bit how I handle ties in rank orderings as a sort of separate side topic. And then I'll show how this whole approach applies to the alpine skiing downhill data. So that's where we're going. So the motivation for all this is the alpine skiing women's downhill. Just to give you a little bit of a sense for how what ends up happening in a downhill trial, here's Lindsey Vonn. So I believe this was back in the Sochi Olympics. I'm guessing this is faster than people who are driving from St. Paul to get to the conference. Almost done. All right, well, that was pretty fast. And she was pretty happy with the result, as she should be. So the way these competitions are set up is that they are measured for the time that they complete the track, but the way these events are actually scored is not based on exactly on time. They basically take a look at how the finishing times and then rank order them and then assign points to the place that they finish and then basically summarize across several different trials. I'll mention some of the details very quickly later, but I wanted to just make it clear that the outcomes for the purposes of scoring these competitions is not based on the time to finish the track. So the data that we're working with was given to us by the U.S. Olympic Committee. There were the data that we were working with spanned from 2002 to 2013, and they gave us a little bit of extra data for 2014, which I'll be showing you the application of for making predictions. So this consisted of basically 12 years of data for 268 skiers, women skiers. What we did, and I'll come back to this assumption later as well, is that what's going to be underlying the model is that the skiers have abilities that are possibly changing over time, and we explored different intervals of time over which they might be changing. What we did is we ended up deciding on 6-month intervals as the amount of time where a skier's ability is not changing appreciably, but there might be some change from 6-month period to 6-month period. So that's how we were dividing up the 12-year period. So we have a total of 24 consecutive time periods over which we think skiers' abilities might be changing. We checked these assumptions using like 3-month periods and year-long periods and found that 6-month actually behaved the best. For each of these 6-month periods, we would, in the data set, we would have anywhere between 0 and 7 events, typically with about 4.5 events per period. And the events varied from anywhere between 8 competitors for smaller events to 66 competitors for some of the larger events. And here's just a histogram showing you the number of competitors per event. So it's more common to have somewhere between like 50 and 60 athletes, skiers per event, than it is to have some of the smaller numbers. Okay. So let me jump right into the model framework. And so here's where I'm going to start to get a little bit technical. So the way to understand the statistical model is to think about each individual skier having an unknown strength of their, basically an unknown descriptor of their ability as just a single number. And what I'll do is I'll denote their ability for skier I at time t. So I is going to index the individual skier, so I is going to go from 1 to 268. And t is going to be the time period, which is going to go from 1 to 24, that's going to index their strength at that particular time. So I'm assuming that at any given time period and for any individual athlete, skier, there's going to be some unknown ability that they're going to have. And I'm going to relate it back to the data in a moment. There are two features of the model that I'll be incorporating. The first is to say that if I happen to know what all the skiers' thetas were for a particular time period, then I should be able to come back to you and say, here's the probability of any particular rank ordering that could happen among the competitors. So if I knew the thetas, I will be able to tell you the probabilities. The problem of statistical inference is that if you tell me the rank orderings, I should be able to hopefully infer what the thetas are for that time period. So that's the name of the game here. So this is just a way to connect, and I'll show you the details in a moment, but I want to connect the data to the thetas for that particular time period. But then there's the question of what do I do about the thetas evolving over time? So that's the second part of all this, which is that I'm going to be making some kind of assumption about the model about how the thetas are changing over time. And that's going to follow what's called a stochastic process. So the two components to the model are a model for the rank orderings if I knew what the thetas were, and I have to be able to say how the thetas are changing over time in some kind of random fashion, so that I actually have some connection between the thetas at the current time period and the thetas at the next time period. Because I don't want to say that they're completely disconnected. If I'm one of the skiers and I have some ability in the January to June time period, I want to assume that whatever my ability is from July to December, it should be not too far away from what it was in January through June. And that's what I'm going to build into this model. Okay. So let me get into now some of the specifics. All right, so the first part I'll focus on is the rank orderings if I knew what the unknown strength parameters were, the ability parameters. So the best way to understand this, and this is actually a very common theme in a lot of the work that I do, is to think about the idea. So forget about the rank orderings for a second. Like, basically you see a race and you see a rank ordering come about. But then if you think about one level deeper, you might think to yourself, well, one way that you can get a rank ordering to come about is pretend as if each skier, or whatever the race happens to be, any kind of athlete, you pretend as if each individual skier, when they're going into the race, produce some number where the higher the number is, the better the performance they had. So the idea would be something like, I don't know, like in competing for scholarships. You can imagine as if each individual that's competing for a scholarship could end up having some score that they would end up getting about how good they are and how deserving they are of getting the scholarship. And for sake of discussion, pretend as if you don't actually see that number. But the way that those scores are going to be used is to determine the rank ordering. So if I knew what those numbers were, those scores were for each individual competitor, then I could just write out the rank ordering, just ordering those competitors from the highest to the lowest. So the idea underlying these models is to basically say that there's some latent score that you don't observe that's like on a continuous scale, which is essentially a performance that each individual skier is generating. And the idea is that the higher the score, the higher this latent score, the more highly ranked they're going to be. So I'm going to call this YIRT to be latent performance, basically a continuous number in event R during time period T by competitor I. And the higher values are consistent with better ability, so those are going to be more consistent with these thetas being higher. And so what I'll do is I'll suppose that for this event that I can basically rank order those latent scores. And essentially the model is going to be, so what this is basically saying that is if YIRT is bigger than Y2RT and so on down to YNRT, what I'm essentially saying is that the rank ordering you're going to observe is that competitor 1 comes in first place, competitor 2 comes in second place, and so on. They're going to be rank ordered according to the order of these Ys, from highest to lowest. Okay? And what I want to do is I want to be able to learn about the thetas from the rank orderings through the latent, but I'm going to learn about them through some assumption I'm going to be making about these latent performances. So what I need to do, since you don't actually observe those latent performances, you never see them, that's like another construct that I have to create for you, I'm going to assume that they're coming from a probability distribution centered at a value that makes sense. So here's the basic idea. I'm going to be assuming that if I'm one of the skiers, that I generate a performance for any particular race that comes from a probability distribution that looks like this. I'm willing to bet most of you have never seen this before. Probably a lot of you have seen normal distributions, and that would be a good candidate to use for this kind of analysis. But the idea is that I'm going to be generating, like when I'm about to play, go into a ski competition, when I'm going to go down the slope, I'm going to generate a value from this distribution. The key is that the center of this distribution is going to be my value of my theta. So if I'm a competitor that has a high value of theta, I'll be typically drawing values that are relatively high. If you're a competitor, if you're a skier that has a small value of theta, or negative value of theta even, then you're going to generate most likely a value of y that's going to be less than mine, in which case the likelihood is that I'll outperform you in the race, and I'll be ranked higher. So the key idea here is every competitor is drawing a latent performance separately from a distribution that looks like this, but just centered at a different place. And the goal here is that if I want to write out the probability of a particular rank ordering, this doesn't have a highlighter, does it? Is that a no? I'll pretend that's a no. So if I'm interested in the ordering that one comes higher than 2, then comes higher than 3, then comes higher than 4, and so on, that's the same thing as if I were to say, what's the probability that skier 1 generates the value y1 that's higher than competitor 2 generating the value y2, and so forth, that second line that says the probability. And then there's a rule in probability, which is often called the multiplication rule, that tells me how to factorize that probability statement. It's essentially the probability that competitor 1 comes in first place out of all the competitors times the probability competitor 2 comes in first among competitors 2, 3, 4 up to n times the probability competitor 3 comes in first among competitors 3, 4, 5 up through n, and so on. So it's this product of what's often called telescoping probabilities. And if I'm going to use that distribution I showed you on the other page called the Gumbel distribution, I actually get a lot of mathematical simplification, and I end up getting an expression which looks like this. That might look annoying, but it's actually relatively easy to work with. It's a product of what's often called multinomial logit probabilities. If I had taken the decision to work with a normal distribution earlier, I would not be able to write any of this down. It would just be impossible to write down. So part of the reason for using that distribution I showed you on the last slide, that Gumbel distribution, is for mathematical convenience because I get a lot of simplification and I'm able to write out the probability of that particular rank ordering. So where are we? Basically what I've done is I've used this trick to generate these latent performances that are going to allow me to compute a probability of a particular rank ordering, and this is what the form looks like. And it's as a function of the thetas. So what this tells me is you give me the thetas for a particular time period, and if you want to know what's the probability of a particular rank ordering, there it is. I can compute it pretty simply. Okay. So that's the probability model for rank orderings at a fixed point time t. So the second piece I need to tell you is how do the thetas change over time? And right now I'm going to invoke an idea that's very common in Bayesian statistics, which is to put probability distributions on parameters. So what I'm going to assume is that suppose I knew my strength like right at this point during this 6-month period, and I wanted to think about what's the possible strengths that I could have in the next time period. What I'm going to assume, which is a very common assumption in Bayesian time series models, is to say that whatever my strength is at the next period of time, the way I get there is by starting off where I am right now and then jumping to another value, but it can't be too far away. In fact, the amount that it's going to jump is governed by a normal distribution with a variance of tau squared, where presumably tau squared is going to be sort of a smallish number. So just in kind of the most extreme case, if the variance tau squared is 0, then it basically says that whatever my strength is right now, the next time period theta is going to be exactly the same. The worst case scenario is that if like tau squared were enormous, then it basically says that my next time period theta is going to be completely separate from what my time period theta is right now. Tau squared is going to be a number that I'm going to need to estimate, and it's likely going to be somewhere between 0 and enormous. And so that basically means that I'm going to have some probabilistic connection between theta now and theta at the next time period. And it's almost like putting a rubber band on the theta so that they don't gravitate too far away. Okay? And then I actually use an extra constraint to say that the sum of the thetas is 0. That's just a constraint I need to impose because I never actually learn, like if you told me all the thetas were centered around 5 and distributed in a certain way, or distributed around -10, that's not going to impact the probabilities from the rank-ordered logit model. So I'm just imposing a constraint on the thetas just to anchor it somewhere, and that doesn't actually affect the probabilities from the model. The one other thing I need to tell you is basically initializing where the thetas are at the first time period. So I'm going to place what's called a prior distribution on the first set of thetas, and they're going to be centered at 0, and the variance of how the thetas are scattered is going to have a variance of sigma 1 squared. So there are two variance parameters that are going to be floating about here, and I'll be referring back to them, and I want to make sure that you understand what their purpose is. Sigma squared 1, the second one, is basically saying when skiers start playing in 2002, how spread out are their abilities? That's what that variance is telling me. Tau squared is a different variant. It's essentially telling me how much can I expect an individual's strength to vary from 6-month period to 6-month period. So that's a completely different variance. But I'm going to need to estimate them in the model fitting process. So that's the model. So I basically described to you the probability for rank orderings given the thetas at a particular time period, and I've also described to you how the thetas are changing over time. What's left now is if you give me data, how do I estimate all of the thetas? How do I estimate the parameters and then use it to make predictions and so forth? So there are two approaches to estimating abilities that I'm going to show you. One I'm going to go through pretty quickly because it's not particularly novel, and then the other part I'll go through it a little bit more slowly. So there's the full Bayesian approach using Markov chain Monte Carlo simulation from the posterior distribution. I bet you Mark Gorman really liked that statement. So there's like the classical approach within Bayesian statistics, which I can just basically apply off-the-shelf software and solve the problem, done. It's a principal method to estimate abilities over time. The bad news is that it's very computationally intensive because you're trying to estimate so many parameters over so many time periods, over so many players. This is an iterative procedure, and it just takes a long time to converge. What I will be focusing a little bit more of my attention on is this approximate Bayesian rating system, which approximates, so the underpinnings of this whole process is, recall that we had that product of probabilities that gives me that rank ordering. What I'm going to do is I'm going to approximate that product as a function of the thetas by a normal distribution. That sounds kind of like a kooky thing to do at first glance, but actually that's a very standard thing to do when you're performing statistical analysis. If you think about the analyses that you perform generally where you're coming up with estimates of, say, like regression coefficients, and then you also get standard errors, effectively what you're doing is you're pretending as if you're working with like a normal distribution of your estimates, and the standard errors are basically telling you, like in a symmetric way, how far the estimates are away from the truth, and you're basically doing the exact same thing. So there's nothing really that controversial about what I'm describing. I'm just describing it in words that are more suited to Bayesian statistics and not to probably material that you've seen before. So the bad news is that ability estimates may not be particularly as reliable as in that first approach, which is completely standard. The good news is that it's very quick. So making these approximations speeds up the computation. So let me just dispense with the full Bayesian version. This turns out to be a very special case of Bayesian inference for dynamic multinomial logit regression models, and there's literature on this stuff, so it's not like it's anything new. So you can fit these models using standard software. The software that I use is called JAGS. Just another Gibbs sampler. It's in the world of WinBugs, if anyone has heard of WinBugs. So just a couple implementation details for those of you who are interested. ran a couple simultaneous chains to disperse the starting values. You run a burn-in of 10,000 iterations, save the last 20,000 iterations for inferences, and only kept every fifth iteration of this procedure because that reduces the autocorrelation among the samples. These are technical details, but this is basically just letting you know that we basically proceeded to get a Monte Carlo sample from the distribution of the thetas that I'm interested in summarizing. Okay. The problem, of course, is that this is very slow on a pretty sophisticated laptop. It took about 2 days to complete the analysis, so this doesn't scale up very well. On the other hand, the rating system procedure is a little bit more worthwhile putting time into. How am I doing on time, by the way? I guess forever. 8 more minutes? 15, okay, thank you. I wasn't talking that slowly. All right, so let me describe the development of the rating system. So the attitude of the rating system, rather than trying to estimate all of the strength parameters across all time, all simultaneously, what I'm usually interested in is adaptively estimating the thetas going forward in time. So the idea is that my first goal is I get the data from the first 6-month period, and then I want to estimate their strengths at the end of the 6-month period. Then I observe the second 6-month period, and then I want to update the strengths from the end of the second 6-month period. And just do that adaptively. So I'm not actually interested in learning about the strengths of the competitors at the start of the period. What I'm really focused on is trying to get the estimates of the abilities at the very end of the 12-year period. If I want, it would be nice to have a mechanism to be able to go back in time and get better estimates of what the strengths were earlier based on later results. And given my time constraints, I'm not going to show you that in detail, but I'll just mention it. But ultimately, if I can do this like kind of forward recursive algorithm where I observe data, I update the parameters, I observe data, I update the parameters, and do that in cycle, then I might be in good shape to be able to come up with strong, good approximations for abilities at the end of the 12-year period. And that's what I'm interested in showing you. And that's, by the way, what all rating systems attempt to do, including the ones that I've developed for head-to-head competition. So I want to update the distributions of the thetas over time as the new competitions come in. I can't realistically perform MCMC after every competition because it just takes a long time. So the alternative approach is to perform what's sometimes called approximate Bayesian filtering. So let me describe the procedure. So here's the idea. So first of all, I'm going to need to estimate those two variance parameters, which I'm putting up here as the square root of them, standard deviations. So I need to do some procedure to estimate tau, the amount of change, what governs the change over time of the competitor abilities, and the sigma 1, which is the spread of competitor abilities at the start of the time period. And I'm going to treat them as fixed and known as I continue to update the thetas over time with new competition data. Then what I'm going to do is I'm going to successively update the distribution of the thetas after competition data are observed and get the distribution for the strengths at the next time period. And then if I'm interested, which I claim I can do, but usually it's not very central, I can do what's called smoothing going backward in time. I can estimate the strengths at the earlier time periods based on data that occurred later. I'm not going to focus on that so much. Those are really the first two bullet items that I'm mostly interested in. So here's the rating procedure in a little bit more detail. So what I'm going to do is I'm going to start off by putting myself in the start of one of the time periods. So right now, at the start of the time period, I'm going to assume that I have the competitor abilities, all of these thetas, are going to be described by normal distribution. So the state of knowledge of what the strength parameters are can be described as normally distributed, centered on some value that kind of says on average how good they are. And then there's some standard deviation, and that standard deviation tells me how uncertain I am about their ability. So everybody's going to start out with a normal distribution of their unknown theta at the start of the 6-month period. Then what happens is I observe competition data over the 6-month period, and then I perform some Bayesian magic that's going to give me some computation that tells me what the normal distributions of the competitor abilities are going to be at the end of the 6-month period, based on the competition data. And so I have what's called the posterior distribution of competitor abilities at the end of the 6-month period. But then I need to do one more thing, which is to recognize that competitors' abilities are changing over time. So then just a couple details on this. So again, in the interest of time, I won't go through the details, but the magic in this step is to find the mode of the posterior distribution and then approximate the log of the posterior density at the mode, and then I need to find the negative of the Hessian matrix and then invert it, and that's going to give me an approximation. Those are details. You can read the paper if you're more interested in those details. But the last bit, after I get the normal distributions at the end of the 6-month period, is then I have to account for the fact that players' abilities are changing over time. So I have to modify the distribution of the thetas at the end of the 6-month period to make it appropriate for the abilities at the start of the next 6-month period, which basically amounts to making the variance larger, inflating the variance. So again, there's some technical details, but the upshot is that the prior distribution for the next 6-month period can be gotten from the posterior distribution of the current 6-month period by essentially adding tau squared to the variance. So if you could see up here, it's a normal distribution with the mean of the posterior distribution, but then the way that I got the variance was I added tau squared to the variance from the previous 6-month period. So actually, it's a very simple addition. And again, the details are in the paper, so I don't want to bore you too much. So that is the algorithm. The missing piece in all this is that I don't know what tau and sigma 1 are. And the way that I'm going to get at them is to perform essentially a predictive validity analysis. And basically, what I'm going to do, and I'll describe it in words before I show you the details, is I'm going to take this 12-year period, and I'm going to run this. I'm going to think about candidate values of tau and sigma 1. So I pick 2 values, say, for tau and sigma 1, and then I run this procedure I described in the previous slides up through, say, 75% of the time periods. And then for every single competition after that first 75%, I'm going to see how well the model predicts on the next competition, and save that, and then move forward in the next time period and see how well it predicts on the next set of competitions, and so forth. So I want to get a measure of how well these thetas are predicting going forward, basically predicting not using that data to build the thetas on. So that's essentially what I'm doing, and there's a particular way that I can do that. So for every candidate, sigma 1, and tau, I can do this kind of predictive exercise of seeing what's the performance of this rating system with the particular sigma 1 and tau. So you might be thinking to yourself, and it basically uses calculating rank correlations between the prior means of basically an estimate of the thetas and then the actual rank ordering. So you can imagine you can rank order their abilities before the event, and you can rank order their actual outcomes, and then you could see how well correlated they are. And that's essentially what the measure is based on. One thing that might sound kind of puzzling is that, well, I basically was describing this as saying, well, there's, you pick a sigma 1 and a tau, and then I can get this measure of performance, but aren't there a lot of sigma 1s and taus you got to select? Well, you can automate that part. And so you can automate it by using basically an automatic optimizer, like there are algorithms out there like the Nelder-Mead algorithm. There are gradient-based algorithms you can use. So you can actually automatically figure out adaptively what the best set of optimizing sigma 1 and tau are without having to just have candidate values and guess them. So that's part of the algorithm. Okay. So that's it. That's the whole algorithm. In the interest of time, I'm just going to flash through these. There's an algorithm that allows you, once you've been able to come up with the theta, the estimates of the thetas, given data that's only prior to it, there's a way to actually get estimates of the thetas using the entire data set, and that's a procedure called smoothing. Again, I'll just flash that by you. There's an algorithm that goes back to the 60s called the Rausch-Tung-Streibel algorithm, which allows you to go backward in time. The details are in the paper. And again, I won't bother you with the details here. So I want to just wrap up by just mentioning some limitations. How am I doing on time? 7 more minutes? OK. Because I want to just very quickly talk about ties, and then I'll talk about the results. So some limitations of this, that the rating system is not fully efficient compared to the full classical version. You're actually ignoring a fair bit of information. So for example, you're not, in this approximate version, you're not saving any information about like how well I've done against one opponent and how well they've done against another. I'm not retaining that information over time. Also, that normal approximation that I mentioned that's at the heart of the algorithm is poor if you're working with a very small number of competitions. It turns out that's not quite so critical here because we actually have enough competitors per competition that the normal approximation is actually pretty good. And then the other annoyance is that unlike the full Bayesian version, where you're estimating every parameter in sight simultaneously, this procedure requires you to estimate tau and sigma 1 first, fix them, and then work on the thetas, work on the strengths. Okay. So the last technical piece I'll mention is that there are ties that occur in these kinds of data. So basically about 9% of the competitors in all these races didn't finish. And that's partly by virtue of the way they score these events. Like if you're not in the top 30 at the end of the whole competition, you're listed as did not finish. You don't actually get a score. Yeah, you don't get a score in some of these events. They're not all of them. There are also instances where you can get a tied ranking, and you might be thinking to yourself, well, if they're measuring these races based on the time it takes to go down the slope, and they're skiers that are tying, they must have really bad clocks to measure. Like if it's if one skier finished 4.9283 seconds and another one finished 4.9283 seconds, that's pretty remarkable. But the way, as I mentioned earlier, the way these events are scored is that they get points allotted. So if you come in on an individual trial, if you come in first, you get 100 points. If you come in second, you get 80. If you come in third, you get 60, and so on. And then you end up summing your best 3 trials. So you can imagine there's opportunities for getting tied scores from just like sort of the cross summation of some of these very discretized points. So it's not uncommon to see ties and then people that just basically finish at the end or don't finish a race at all. So I'll mention pretty quickly that that this whole model doesn't lend itself very easily to ties, but there is a gold standard which is I guess again in the interest of time, it's very complicated. Just to give you a flavor of what you actually would do in like, the right way to handle this. Suppose you have competitors 1, 2, 3, 4, and 5. Say competitor 1 comes in first, 2, 3, and 4 tie for second, and 5 comes in 5th place. The right way to bring this into like a standard analysis is to replace that product of those terms that looked like e to the theta over the sum of a bunch of thetas. We basically had a product of a bunch of terms. You're going to need to replace that with an average of the contributions if the order was 1, 2, 3, 4, 5 plus 1, 2, 3, 1, 2, 4, 3, 5 plus 1, 3, 2, 4, 5, and so on, and then average the sum of those products, and then you have to perform all your analysis working with sums of products of things. And if any of you have worked on statistical inference where you're multiplying products, essentially sums of products of sums, it's a holy nightmare. So if there's any way to get around it, you would want to. Turns out that within the Bayesian approach, there's a nice way of handling it. So the good news is that you're essentially, if you did what I just described, you'd be able to estimate the thetas in a principled way. The bad news is that even with a couple of ties, it's just a computational nightmare. So the way that we do it is in the full Bayesian version, at every iteration of Monte Carlo Markov chain sampling, you just permute the indices of those who tie, and then that's basically solves the whole problem. If you want more details, read the paper. In the approximate Bayesian version, I do something that resorts back to an idea in 1974 by Breslow and Crawley. And essentially what they do is they, in this example that I just described, what I basically do is I say for competitors 2, 3, and 4, I replace their versions of the factors in the product with pretending as if competitor 2 defeated 2, 3, and 4, but then also have a term in there where competitor 3 defeated 2, 3, 4, and 5. I forgot 5 did the worst, so I got to include 5 in there. And then the last term is that competitor 4 did better than 2, 3, 4, and 5. So I'm acting as if each of those competitors involved in a tie did better than everybody else, including the ones they tied with, and that comes into the equation once. Anyway, more details in the paper, but I just wanted to alert you to that idea. All right, so finally some results. I'll speed through this to get to the end. So in the full Bayesian version, you can estimate those standard deviation parameters. Basically, what you get out of this is that the variance in abilities changing over time is very precisely estimated, although you get different answers whether you do the full Bayesian version versus this filtering algorithm. Sigma 1, the amount of spread in the abilities is not very well estimated, but in some ways that's not a huge shock because it's very hard to estimate the abilities of these skiers at the start. This is the distribution of what the mean abilities are at the start of 2014, and you could see that that this distribution ends up having some of the skiers be particularly strong, which is shown by this right skew distribution. This is basically the rank ordering at the end of 2013 based on the fully Bayesian version and then the approximate Bayesian version. They actually line up pretty well. There's only 1 or 2 instances where the approximate Bayes version is not in the same order as fully Bayes. One such person is this Lara Gut, probably Gut. But they're additively off by about 0.4 in each case, but they do line up to be about in the same order, which is somewhat reassuring. Just to finish up the analysis, I wanted to show some particular results for 2 American skiers, Lindsey Vonn and Julia Mancuso. This is essentially showing the abilities, the estimated abilities of Vonn in blue and Mancuso in red using the fully Bayesian version, and then this is using the approximate Bayesian version. So the blue is following Lindsey Vonn over time. She ended up getting an injury, I believe, in 2007, which explains why it goes up and then comes down. She wasn't performing as well, but then all of a sudden, in around 2010 or so, she just was doing amazingly well and just had an incredible performance. The dotted lines, by the way, are essentially the equivalent of standard error, like 95% confidence intervals. So it's 95% credible intervals around the estimates. And then meanwhile, Mancuso's getting better over time. Generally, had a little bit of a dip in 2009, but what is remarkable is that they actually look to be they have the same shape, the same trajectory, whether you're using the version that's based on fully principled approach versus the one that does all these approximations that's very quick. In fact, you can actually calculate, if you pretend as if Lindsey Vonn and Julia Mancuso were the only 2 people involved in races, and you wanted to calculate the probability that Vonn would outperform Mancuso using each of those 2 different procedures, this is how that probability changes over time using the model results. And they actually track extremely well, which is to say that the approximate version seems to be doing pretty darn well. I'll just mention again in finishing up that they are predictively accurate. You can do this correlation idea I described based on the data from 2014 that we collected over just a few months. These are Spearman correlations, and they're extraordinarily high, basically saying that the estimated abilities correlate pretty highly with the rank orderings from these races in 2014. So that's really good news. So just by means of conclusion, this is that the fully Bayesian version could be implemented by MCMC, but it takes a long while to actually run the thing, and it doesn't scale well. The approximate version is a realistic, practical version for ongoing estimation in leagues and sports. There's a way to handle ties that can be incorporated to both of these approaches that doesn't degrade the systems at all. And this is the paper that where the paper appears. So it's at the end of 2015. I will mention that to really wrap up, that the U.S. Olympic Committee basically, had us develop this algorithm, and we gave them the code to run the algorithms. And apparently they got hold of other similar algorithms to handle rank orderings. There's this Microsoft TrueSkill system that does the same sort of thing. And there's some other algorithms that people have developed. So the U.S. Olympic Committee came back to us a couple months ago, and they said that this, they applied this to the Rio Olympics, and they said they were just like dumbfounded how well this did in predicting results. And now they're hiring us again to do some more work. So that's the real proof that this is good stuff. So thank you very much for paying attention.